you are designing a small cavity which contains air between two horizontal plates, each with a surface area of 1 meter squared. The plates are 8 mils apart from each other, and you may also assume a plate length of 8 mils in the direction of interest. So first things first, small cavity. This is indicating to you this is a enclosed space. Okay, this is a fine print for enclosed space. And on the direction of interest, it's pretty much telling you on the direction of the thing of your characteristic length, right? So if your characteristic length was, I don't know, length, then it will be 8 mils length. If it was diameter, it will be 8 mils diameter. The bottom plate is held at 500 and the top plate is 300 Kelvin. Determine the heat transfer in watts. So it wants us to determine Q. And we can do that by doing this. And we need to find this to be able to do that. And then B, assuming you have one encrypt. Okay, so B is completely different. So let's wait for B later. Let's first find Q. So this is the situation we have. We have two plates, okay, one on top of the other. They are 8 mils apart. They are both 1 meter squared area. And they are 8 mils in length as well. The bottom one, according to what is said, is 500 Kelvin, and the top one is at 300 Kelvin. So we know there will be Q flowing from the bottom one to the top one, just like we would expect, right? Being in enclosed space, this is the general equation you'll be using for enclosed space situations for natural convection. And just like the previous one, we also have the Rayleigh in between, and we have 3 coefficients. Now we have C, N, and M. The L, in this case here, that will be along the surface. So L will be this guy here. And this delta here will be between the surface. So it will be this guy there, right? So between the surface delta and along the surface L. Okay, how are we solving this? Well, it's pretty much, we're grabbing this equation, we're solving for Nusselt, then grabbing H and solving for Q. To solve for Nusselt, we need to find what are those coefficients, the C, N, and M. And I'll be looking at this table here, 7.3. This is a photo from my notebook, which is a scan from the actual book. You should have this table on your lecture slides, okay? So you don't have to rely on this. But we have 2 horizontal plates. We're dealing with air, so we're not interested in the fluids one. So the liquids one. So this we can disregard. So we're dealing with air, and we have horizontal plates. So this is our situation here. Heating from below. Okay, so that's our case. We're happy with this table. And what we need to do is figure out what is our Rayleigh number. And depending on the Rayleigh number, we're going to have to use this, or this to solve our question. All right, now it's going to give us a Prandtl, and that's also going to give us C, our N, and our M. Brilliant. So I'm grabbing properties for air. That's table A5. And I'm grabbing properties for T-film being between 300 and 500. So T-film is 400, right? So T-film equals 3 plus 5 divided by 2, which is 400. Okay. These are the properties at 400. Note that I grabbed the properties to calculate our Grashof, just like before. And also note that we do have an ideal gas. Again, we have air, so we can do beta as 1 over 400 as opposed to using the big chunk from the right part of the table. Okay, so let's jump straight into calculating Grashof. Gravity, 9.81 times beta, 1 over 400 times delta T 500 minus 300 Kelvin. Characteristic length, they told us to consider 8 mils on the direction of interest to the third. And I'm dividing everything by my kinematic viscosity. Okay, so like on the previous example, instead of using density and the dynamic viscosity, I just used the kinematic viscosity. Hopefully this is right, and what I got was, let's see, 3,740, approximately. It's 40 something. Okay, so if that's the case, then our Rayleigh number is pretty straightforward because we just need to multiply our Grashof by our Prandtl. Prandtl being 0.609. So this becomes 2576.25. Oops, 2576.8. Okay, cool. So now we can go back to the table and figure out in which situation we fall under. And we fall under, so no greater than this, and we're smaller than this, we fall under this situation here, right? So check, oh good. So if that's the case, then our Prandtl is between 0.5 and 2. That's correct. Our Prandtl is 0.68, so all good. And if all these check, then that means that our C is 0.059, our N is 0.4, and our M is 0. So let's solve for Nusselt. You grab this equation. Zero 0.059. Grashof times Prandtl, that's Rayleigh, right? So 2576.8 to the M, OSM 0.4. And then inside here we have the distance along the plate. It doesn't really matter, right? It's going to cancel each other about, but let's put it anyhow. And the distance between the plates is 10 to the minus 3. But this is to the 0. So even if they were not the same, it'd be 1 by the end of it. Nusselt equals 1.3655. But we know Nusselt is also equal to H, characteristic length K. In this case, this is 8 mils, right? So 8 mils. And therefore, my H is 5.74. Okay, so if that's the case, then calculating my Q is trivial. It's this times this times this. Our area is 1 meter squared according to the problem. 1 meter squared, that's fine. Our delta T is 500 minus 300, and our H, we just got our H. So 5.74 times 1 times 500 minus 300 Kelvin. 1149 watts. Okay, so that's the answer for part A, right? Part A. Cool. Let's jump ahead and see part B. What does a part B say? Assuming you have won a trip to the station on the moon held at Earth's atmospheric pressure, and you take your design with you, recalculate the heat transfer rate and assume that the moon's gravity is 16% that of Earth's. What change in your calculation? Okay, so same atmospheric pressure, but now, so let me go ahead and undo this because we're going to have to go back to this. Let's do part B. So part B, at moon. Well, we still need to grab our properties. It's still air, so it's still air. We're still looking at properties at 400 because the temperatures did not change, and pressure is still on atmospheres. So under those conditions, everything here is going to be the same, right? All these guys here will be the same. Copy. So when I calculate Grashof, however, let's put it in red here, but G at moon equals 16% G at Earth, right? So when I calculate Grashof, everything will be the same except for my gravity, right? So these guys are all the same. The only thing that changes is my gravity. So that means that I can conclude that the Grashof at the moon equals 16% that of Grashof Earth. Right, so I can pretty much take the number that we had before, which was, let's see, what is my Grashof? 3740, multiply that by 16, divide that by 100, and I should get the Grashof at our space station. Right, let's do that. Four hundred, 598. Okay, so only 16% that we had originally. And if that's the case, we can calculate Rayleigh. Rayleigh is going to be a new number, not because Pareto changed, but because Grashof changed. And Rayleigh becomes 412. Okay, so now we're going to go back to our table and see what's going on. Still air, still horizontal plate, all that's the same. But this is not the case anymore. This is the case. Right, we have 412, so it's smaller than 1700. So that is the case there. And if that's the case, then that means that there's no coefficients for it because Ke over K equals 1. And remember what I told you guys? The apparent conductivity divided by the conductivity is the same thing as Nusselt number. Right? Same definition as Nusselt number from this set of equations here. So what this is telling us is from the table that we get that our Nusselt number, we don't have to calculate Nusselt because Nusselt is 1. Under these conditions, Nusselt is 1. And if Nusselt is 1, what does that mean? For those of you who've been paying attention in this unit, okay, so if our Nusselt number is 1, our convection is not assisting in heat transfer, right? Which means that our dominant heat transfer mode is conduction, right? So if I go ahead now and try to calculate Q like so, that would not work out, right? Because this guy doesn't really make sense to use. This guy doesn't really make sense to use because conduction is dominant, not convection. So what do we need to use instead of Newton's law of cooling? Fourier's law, remember? The conductivity of whatever we're dealing with, the area through which energy can be exchanged, the delta T as per usual, and the distance it has to travel. And I'll jump into more details about this analysis that we're doing in just a second. Let's just calculate it first. What is K? 0.03365. Area 1 meter squared. Delta T 500 minus 300. And the distance it has to travel is the distance between the two plates, right? Don't forget our first analysis. What we knew from the start was happening was that Q was going from this plate to that plate. So the distance they have to travel is 8 mils. This number hopefully will be smaller than the previous one, 841. What was the previous one? Forget.
1,148.
There you go. I haven't thought so. It's indeed smaller, right? So we don't have that push due to convection anymore. You can think of it sort of that the extra 300 watts that we had on the previous situation A, was the enhancement due to convection, right? It's not quite that, but you can think of it that way. if it helps you out. Now, I want to talk to you guys about, I might stop the video here because the question is over, but I want to talk to you guys about the heat transfer.